All right, I want to give a couple more comments dealing with just basic antiderivatives before we move into a little bit more complicated situation of taking the antiderivative of a function. The situation that I want to talk about is the application that this has in the physical sciences, because this is where a lot of these antiderivative problems are generated from. Okay, and I'm going to take this first example here. It says, suppose that the velocity of a function at time t is given by this equation, 6t squared minus 2 divided by t. 2 divided by t squared, I guess. Okay? And it says s of 1 equals 8. And they want us to find the original position function s of t. Okay? So here's what this question deals with. Now, I need to go through and remind you of what all these variables stand for. Okay? In physical sciences problems, the t usually is some time component. Okay? We don't know if it's in hours or in minutes or seconds or whatever, but it is some time variable here. V is the velocity variable. Okay? So we're going to say that if we plug in a number for t into this function, that it will tell us the speed of the object at that time. Okay? The s that they talk about usually is called the position function. Okay? So if I take and look after 1 second, the object should be 8 feet down to the right, or 8 miles down the road, or whatever this question, whatever the label is in terms of position. So this is telling me after 1 unit of time, I am 8 units in terms of position. That's where my location is. Okay? Now, the relationship between these two functions, v of t and s of t, that's what I need to tell you here. Okay? In that when we had an original function and we took its derivative before, what did the derivative tell us? The rate of change, and the rate of change is like a velocity function, right? Okay? So the derivative of the position function is the velocity function. If we're talking about something speed, we talk about it in miles per hour or feet per second or some label like that. That's a rate of change type label. So the position function's derivative is the velocity. Okay? Now, what's important about that is that what if I take the antiderivative of the velocity function? If I take the opposite, not the derivative, but the antiderivative of this, shouldn't that take me back to the original function? So, and this is what I'm saying. If I take the antiderivative of v, that should take me back to the original position function s of t. And that's what we're trying to do here. We're starting with the velocity. We want to get back to the position function. Okay? So it becomes an antiderivative question. All right? So let's come down here and let's work this antiderivative now. Okay? What's the antiderivative of 6t squared? Okay, so this will be s of t equals 6t cubed divided by 3. Okay, and I know some of you simplify it even quicker than that. Okay, but this will work for now. How do I need to think about this one? Before I take its antiderivative, I want to do what? To the negative second. Okay, so I'm going to think about it that way now. The negative 2 just stays there. And what's the antiderivative of t to the negative second? To the negative 1 divided by negative 1. Sure. And then I've got a plus constant on the end here. Okay? Now I have the original function, but I don't have it quite finished yet because they did give me enough information. They told me that after 1 second I need to be at position 8. So I have the ability to go through and solve for this constant here. I can find out what that value should be. Okay? So the 8 goes in here for the y value, or the position of the object. I plug in 1 for t, okay, and if I clean this up, that just turns into a 2. After I plug in the t, 2 times 1, that's just 2. Okay, here I've got negative over negative, so that's positive. This is 2. 1 to the negative 1 is still 1. Plus constant, so what value do I need to sub in for c to make this equation work? Well, I need a 4, right? Okay, so this tells me that the constant needs to be 4. And so my final answer for this problem would be that the position function is 2t cubed, and I'm just cleaning up some of these divisions here, okay, plus 2 divided by t, and then plus my 4. And again, I'm just rewriting some of this stuff and then subbing in the constant. Okay? So if you get a physical sciences problem talking about the relationship between a velocity function and a position function, now you know how to go ahead and attack those problems. Okay? I won't do an example like this, but I'll mention one more thing, is that we said that if we start with the original s of t and we take its derivative, then that gives us the velocity. What if I take the derivative of the velocity function? What does that tell me in physical sciences? That's acceleration, right. Okay, so we kind of have a progression here. If we start with s of t and we take the derivative of this is the velocity function. And then if we take the derivative of the velocity function, I get the acceleration function, right. Okay, so if you're given anything about acceleration, it's very similar to this process. We would just have to work backwards. If I take the antiderivative of this, I'll get back to the velocity. And if I take the antiderivative of that, I could get back all the way to the position. Okay? So if the question starts with an A and they want to work all the way back to S, you're just going to have to do this process of antiderivatives twice. Work back to get to the velocity and then work back one more step to get back to the original function. Okay? All right, so any questions with those? All right, so just a few basic applications where we can work through these antiderivatives to help us locate some initial values here. All right, the next major concept in terms of antiderivatives is a process called substitution. And this is a way of taking antiderivatives for equations that are a little bit more complicated than the ones that we worked with last time. Okay? Now, the major reason we have this method called substitution is that we need to be able to undo the chain rule. Okay? And this is our way of working backwards out of chain rules and getting back to the original function. It's a little more difficult because chain rules were a little more difficult than just normal power rules in the derivative sense. Okay? Now, in order to do this, though, I'm going to kind of work through something in the forwards direction, and then we'll look at the result and we'll see if we can work it back up to the original function. I think that'll be helpful if we start by doing derivatives first here. Okay? The example that I will use, let's start with this function. Y equals 5x squared plus 3, and the quantity is raised to the 6th. Okay? And so we want to take the derivative of this function. Let's just work it through in the forwards direction, then we'll talk about what it would look like if we went back the other direction here. Okay? Now, we're pretty good at chain rules by now, and I think most of you could see right away that if we did this chain rule, it would just be dy dx equals, the 6 would come out in front, all this power would become raised, or all this polynomial would be raised to the 5th, and then I would look inside, and I would see that the chain rule tells me there's a derivative of 10x on the inside. Okay? All right, so what I'm going to do is I'm going to do a little bit of work with differentials. I'm just going to multiply this dx over to the right side. Okay? And so I get dy equals all of this. Okay, so here's working in the forwards direction. Okay? So now what if I had a question that looked like this? What if it told me take the antiderivative of 6, 5x squared plus 3 to the 5th times 10x dx? Okay? This is what our questions are going to look like here today, and we need to be able to work them back to a function like this. Okay? And so we're going to see a lot of functions today that look kind of messy. You know, they're not the easiest things to start with, and we're going to have, and usually going to be able to come back and get to some fairly nice function at the end. Okay? The first thing that I want to point out is that when we do substitution or undo the chain rule, we usually see a lot of multiplication down here. Okay? We see a lot of things like products of two functions put together because that's what chain rule does, is whenever we do a chain rule, we just multiply a whole bunch of things together. So that's your first clue, is if you see any type of antiderivative where you've got multiplication, that's probably the first thing you look for, is can this be undone with the chain rule or substitution? Okay? Now, how do I know if substitution is going to work when I try to undo this function? Okay? All right. Well, the object of this is to look at the two things that are being multiplied together. Look at the two functions. Okay? We try to see if one of the functions is the derivative of the other. Okay? And as I look at this, I just look inside one of the parentheses and I see that if I take the derivative of this, I get 10x. And so that's my clue as I'm looking at this problem that, yes, substitution is going to work in this example. Okay? Now, later on, what we're going to find out is that this doesn't have to be an exact perfect match right here. Okay? If I see this 5x squared plus 3, and usually they wouldn't have this split apart. Maybe they would have this 6 times 10, and this would be a 60 here. Okay? If this wasn't over here. Is this thing very close to the derivative of this thing? And we can say yes. If the derivative of here is 10x, this is something times x, so it's fairly close. And so later on what we may have to do is we may have to take something like a 60x, we may have to end up splitting it apart into a 10 times 6 so that this is exactly the derivative of this. Okay? So when we're looking at these problems initially, that'll be the first thing we look for. Is just, is one of them the derivative of the other? And if that's the case, then we proceed. And if it's not the case, then we say, well, substitution's not going to work here. Okay? All right, so we know this one's going to work because we actually worked through it the forwards direction. Now, the process for going backwards is this. We make a substitution of variables. We change the variable. Okay? And in this substitution, I'm going to let u equal 5x squared plus 3. Okay? We're going to make a substitution in this because this is a big mess. We don't see the antiderivative. So what I want to do is make this whole mess a lot cleaner. I'm going to just replace it all with u. Okay? So when I get ready to take this antiderivative, the 6 will stay here. This will change and become u to the 5th. Okay? It's just a lot easier to work with a single variable instead of a more complicated function. Now the thing is, though, we just can't arbitrarily sub stuff in and call it good. Okay? What we need to do is we also need, if we're going to replace the x's here, we also need to replace the x's and the dx over here. Okay? So what we're going to do is this. When we make a substitution, we also need to take the derivative of that substitution. Okay? And so if I take the derivative, ignore all this, what's the derivative of this function right here? It's 10x. Okay? If I use differentials and multiply that dx across, I see that du is 10x dx. Okay? Now, as I look at my equation down here, all of this can now be replaced with what? I can replace all of that with du. Okay? So what we'll do is we'll get some of the stuff gets replaced with this, and some of the stuff gets replaced with the derivative. Okay? So all of this just turns into a du. And like I said, I have to replace all the x's with u's. If I'm going to change some of the variables, I've got to change them all. And now I have done that. I've changed this over into a u problem. Now, if you saw this as a problem, this looks a lot like what we did last time. Okay? How do we take the antiderivative of 6u to the 5th? Okay? Well, the 6 just stays there, and then what's the antiderivative of u to the 5th? To the 6th divided by 6. Right, sure. Okay? So u to the 6th divided by 6, and then I got a plus constant on the end. Okay? I can see real quickly that the 6's cancel off, and so I end up with u to the 6th plus a constant. That could be my final answer. Now, usually it's pretty common practice, though, that if we start a problem with x's, we usually want to end up with x's. We don't want to introduce a new variable if somebody may not know what we used for u. Okay? So what we do then is once we've taken the antiderivative, then we come along and we replace the u, we resubstitute, back in this 5x squared plus 3. Okay? So this would become 5x squared plus 3 to the 6th plus a constant. And this would be our antiderivative, and that matches up exactly with what we started up here at the beginning. Okay? Now, this one didn't have a plus constant on the end of it, but if it did have a plus constant, wouldn't I still get the same derivative? Yeah. Okay? So yeah, this is exactly equivalent to what we started with then. Okay? So the process of substitution goes like this. Step 1 is to decide, first of all, if it even works. We look to see, does one of the pieces, is it the derivative of the other one? And then if it is, we make this substitution We substitute in the original and the derivative, and then take the antiderivative of the new variable, because it's usually going to be a lot easier to work, and then finally go back and back substitute in. Okay? All right, so let's look at some more examples here. See how this process of substitution works. All right, I've got a 4, 2x plus 3 to the fourth times dx. Okay, and I want to go through and use substitution to solve this problem. Now, you wouldn't necessarily have to use substitution to do this one, okay? But we'll go ahead and we'll use it so we can get used to the process. Okay? The reason I say you don't have to use substitution is, notice this one had two x's in it. You know, we had an x here and an x here. This one really only has the one variable, so we probably could get away without it, but let's practice the process. Okay? What's the most complicated piece in this antiderivative here? What do we want to let u equal? The 2x plus 3, right. We want to replace this in parentheses with something nicer. So let's let u equal 2x plus 3. Okay? Now, what's the derivative here? du is what? 2 dx, right. And you know, du dx, and then I multiply the dx across, so I get du equals 2 dx. Now, I start looking at my original problem, and I try to start substituting things in. Okay? First of all, if I just do this, this will become what? U to the fourth, right. Okay, so all that becomes u to the fourth. I just replace everything in parentheses with u. Okay, now the only thing that I have left is I have a 4 and a dx left over. Now, do I have a 4 dx to match up exactly here for du? No, I don't quite have that. But what could I multiply both sides by so that it does match up perfect? Multiply everything by 2, right. So if I come in and I multiply this by 2, and I multiply this by 2, now I've got a 4 dx over here. What can 4 dx be replaced with? 2 du, right. Okay, so I can replace this with a 2 and a du. That's how I can substitute everything over, change it into u's, and now, you know, just looking at this, this looks like a much nicer antiderivative than this one. Okay, what is the antiderivative of this? Okay, well, the 2 just stays there, and then what's the antiderivative here? U to the fifth divided by 5 plus a constant. And then to finish off the problem, I just come back and resubstitute in for the u's. Okay? So this will be 2 times 2x plus 3 to the fifth divided by 5 plus some constant. Okay? And if you ever want to check your answer to see if it's correct, if you're not quite sure you've done something correctly, all I need to do is take the derivative of this thing, clean it up, and it should look like this. Okay? And if you've done it correctly, those should match up. All right? So there's one example of using substitution to take an antiderivative. Okay? Let's look at another example here. Let's see. X squared plus 2x minus 4 dx. Now, before I even use substitution, I forgot to do this on the last example, okay? Before I even do substitution, as I look at my two different functions here, I should try to decide, is one of them the derivative of the other one, or is it close to the derivative of another one? Okay? And as we look at this, well, we look at the bottom one. The derivative of the bottom one is what? 2x plus 2. It's perfectly matched up with the top. So yes, substitution will work in this example really well. Okay? All right. So I'm going to replace u with what? Or u is equal to what? Yeah, I want to let u equal the denominator. That way when I take the derivative of it, the du, I get what? Okay, I get the numerator, right. Okay, 2x plus 2 times dx, sure. Okay, and again, I'm going to skip the step of writing du dx and then multiplying it over. I think you should all be able to see that by now. Okay? All right, so now I want to go back and change all this over into an antiderivative in u. Okay? All right. The denominator turns into what? Denominator is just u, right? If I make the substitution, all this is just equal to u. Okay, so the denominator equals u. Okay, now what about the numerator? Well, dx is actually goes with the numerator because it's multiplied by this antiderivative. So this all goes together. It all gets replaced with what? That's all just du, right? Now, I can either put the du up here, or I can just put it out here and put a 1 up here if I want. Okay, because you can always multiply by 1, and I can always do the multiplication out at the end here. Okay? All right, so now I've converted what looked like a messy antiderivative into something that's pretty nice. What's the antiderivative of 1 over u? ln of u. Sure, this is the ln of u plus some constant. And then my last step is just, again, resubstitute in terms of x. So this is the ln of x squared plus 2x minus 4 plus a constant. Now, a common practice when you get to a natural log as an answer here is instead of putting all this in parentheses, it'll be very common for you to see this in an absolute value symbol. Okay? The only reason they're putting it in an absolute value symbol is just to remind you that what type of numbers can we take the natural log of? Well, we can only do positive numbers, right? Okay, and so this is just saying we're going to make sure that this came from a positive result, because if these were negative numbers up here, then this is not a valid antiderivative. Okay, so that's basically all it's saying. So if you ever see this, don't worry about it. You can kind of think about them like a parenthesis almost. Okay? All right, good. Okay, what about this example here? The antiderivative of r times the square root of r squared plus 2 dr. Okay, as I look at my two functions, and I'm calling r the first function, and I'm calling all this the second function, is one of them the derivative of the other one? Or is it close to the derivative of the other one? Okay, well, what is the derivative of r? Derivative of r is 1. Is this close to 1? No, not really, because it's got variables in it. Okay, if I look at the derivative of this one, the derivative of this one is what? 2r. Is 2r fairly close to r? Yes, 2r is very, very close to just r. So I think substitution or undoing the chain rule will work in this example. Okay? All right, so I let u equal what? Always the more complicated piece is the u, so which one is it? The r squared plus 2, right? And then du equals what? 2r times dr, right? Okay, so this is 2r dr. All right, now I start to look to make substitutions. I try to match stuff up here. Okay, when I'm changing this over, I'll start with the more complicated piece here first. Okay, this all becomes what? Square root of u, right? Okay. So this becomes square root of u. Now, the only thing that I have left to substitute for is I have an r and a dr. And that's fairly close to this, but it's not exact. So what do you suggest that I do here to make it match up exactly? Okay, I've got two options here, and I think I heard them both, right? Some of you, I think, were saying multiply by 2. Now, I don't really want to multiply by 2 down here because that'll make this a 4r dr, and so that's not getting me anywhere. But if I do my multiplication up here, if I just multiply and divide this function by 2, that's okay, because now the numerator will be 2r dr. So that's one option. Now, I'm going to suggest something else, though. Okay? Another option is how could if I try to solve this for r dr, what do I need to do with this 2? I could divide it over to the other side. Okay? So if I come in here and I divide both of these sides by 2, now what is r dr the same as? It's the same as du divided by 2. Or in other words, it's the same as 1/2 times du. Okay? And so that's another way. And you can do this either way. You'll get the same answer either way, whether you multiply in the original or if you do the division down here. Okay? I usually try not to adjust the original function too much. So I usually just try to do stuff down here. Okay? All right. And again, this looks like a much more manageable antiderivative than what we started with up here at the top. Okay? All right. The 1/2 just stays there. What's the antiderivative of the square root of u? Well, we want to think about it as u to the 1/2. And what do I get if I antiderivative that? Okay, u to the 1.5 divided by 1.5 plus a constant. Sure. Okay, add a full unit and then divide by the new number. Okay. Now, in terms of finishing this off, there's a couple things that I would do. One is I'd go ahead and clean this up. This is 0.5 divided by 1.5. How many of these go into this? Well, there's 3 of them, right? So this is 1/3. U to the 1.5, I'm going to replace the u. So I get r squared plus 2 to the 1.5, or 3/2, however you want to write it, and then plus a constant on the end. Okay, and so this is the original function, okay, and then this is its derivative up here. All right, so that's another example of substitution. Notice the types of things that we're using substitution on, okay? Polynomials raised to powers, like 4th or 5th power, higher powers. That's a good time to use substitution. Over here where we had logarithm derivative, numerator and denominator, that was another place. Square roots are a good place where this idea of substitution comes into play. Okay, these are some of the more common examples that you're going to see. Now, I want to bring up one more point though, and that is that maybe this question has run across some of your minds, and that is, why don't we in this problem, okay, why don't we let u equal the square root of r squared plus 2? Why did I just stop at r squared plus 2? Why didn't I make it u equals all of this? Because then if I substitute it back in, all this just gets replaced with a u. There's no 1/2 down here on this derivative. Okay? Well, the answer is because if I take this derivative, if I try to calculate the du at this point, I'm going to get a lot more complicated function down here than what I really want. Okay? If I take this thing's derivative, I'm going to have chain rules involved, and it's going to be harder to match this up with what's up here in the original function. Okay? So that's why usually we try not to make the u too complicated. We just try to pick out what's underneath the root, or what's inside the parentheses, or just the denominator, or something like that. Don't make it too complicated, because if you make the u too complicated, then it's going to be a lot harder to match it up and work this process backwards. Okay? Usually we don't want any chain rules on the u. We just want a nice power derivative. Okay? All right, let's look at another one here. Just some different kinds of examples. E to the 1 over z divided by z squared dz. All right, and this one takes a step up, I think, in terms of complexity here. Okay? All right, I need to look at this and just decide, first of all, will the substitution even work here? Okay? Well, if I substitute for the denominator, if I substitute u equals z squared, what's the derivative of the denominator? Derivative of z squared is 2z, and does that show up anywhere up here in the numerator? No. Okay, so I definitely don't want to substitute that way. Okay? What do you think you might substitute for up in the numerator? Do we want to do the whole numerator or just part of it? Just part of it, right. Kind of the same thing I was talking about over here. Okay? Because if we do the whole thing, we start to get too complicated of a derivative in the substitution. So all I want to substitute is what? U equals what? 1 over z. Let's just do the u equals 1 over z piece. Okay? And sometimes you try this. Sometimes it's just a trial and error thing. You try one of the things, and then you take its derivative, and if it doesn't match up with anything, well, then you go back and you try something else. Okay? But I think this time this is going to work pretty well. Because if I think about this as z to the negative 1, okay, what's du? What's the derivative of something to the negative first? Negative 1, z to the negative 2, and then I've got a dz on the end of this, right? Okay, so here is my derivative. Now, does this match up with the denominator somehow? And the answer is yes, because z to the negative second is the same as z squared in the denominator. Right, so we have a good match here. Okay? All right, so now we want to go back and make our substitution. Now let me rewrite this just so it's a little bit easier to see how this is going to all be replaced in the original function here. All right. My numerator turns into what when I change it over to the variable u? E to the u, right. Okay, the numerator is just e to the u because that's what I chose to make as my substitution. Okay. Now, the only things that I have left to replace, I still have to replace all of these. I have to replace a z squared in the denominator and a dz. What's the only thing different about this as compared to what I have up here? This one's got the negative sign and this one doesn't, right? Okay, that's basically the only thing that's different. Okay, so what could I do to try to get rid of this negative sign? Or not get rid of it, but where can I move it? I can divide it over to the other side, right? If I divide this side by -1 and I divide this side by -1, that's going to make this positive and this is going to make this negative. Okay, now I have a perfect match with this and what I have circled up here. Okay, because I can always tack on a 1 up here, that's not a problem. 1 over z squared dz, that's a perfect match with negative du. Okay, so I can put in a negative du right here. Okay, now I've converted this over. This is a pretty nice thing to take the antiderivative of. First of all, -1, this is just a constant. So I can actually take this -1 and I can pull it all the way out in front of the antiderivative if I want. Constants just stay there, and if I want to move that thing away, you know, I have the ability to do that. Okay, now what's the antiderivative of e to the u? What's the antiderivative of e to some number? Just e to that number, right? Okay, so the antiderivative of this is just e to the u plus a constant, and then my last step is just go back and resubstitute in 1 over z. Okay, and so the answer to this problem is this right here. Okay, like I said, that one was a little more complicated because it had the negative powers in it, so we had to be a little more careful when we were doing our substitution. All right, very good. Okay, now the next example here. Antiderivative of 4r times the square root of 8 minus r dr. Okay, now as I look at this problem initially, okay, if I look at my two pieces, what's the derivative of this piece? Is a 4, and does that show up here? No. Okay, what's the derivative of this piece? -1, does -1 show up over here? Well, kind of, but not really. I mean, I have an r here. Okay, so it appears that right away, substitution may not work very well on this example. Okay, but it actually does. If we start to work through the process, we should be able to get this to work even on this situation where it doesn't even look like it works. Okay, all right. What do you think I will let u equal? What appears to be the more complicated piece? I mean, neither one of them's that bad, but probably the part underneath the square root, right? Usually that's what we do. We substitute for things underneath radicals or in parentheses or something, right? So let's let u equal 8 minus r, and then what did we say the derivative was? -1 times dr, right? Okay, so here's our derivative. Now, let's try to go back and start substituting things in. Let's see if we can get this to work here. Okay, I'm going to skip this 4r for a second. This all changes over to what? Square root of u. Yeah, that's the easy part to switch over. It's just square root of u. Now, the things that I have left to substitute for, okay, I have to replace a 4r and I have to replace a dr. Okay, now, usually we try to replace all that stuff at once. Okay, but in this example, I think we need to replace it one piece at a time. What if I just try to replace the dr? Okay, dr would be equal to what? Negative du, right? I can divide that negative over just like on the previous example. So I can replace dr with negative du. And I'm going to put that negative out in front just like I did on the last example. Okay, so I have replaced all of this, and I have replaced the dr. The only thing left for me to replace is the 4r. Now, 4 is just a constant though. Constants can just stay within antiderivatives. If they're multiplied, they just stay there. So I didn't replace the 4, I just rewrote the 4. The only thing that I have not replaced yet is an r. Okay? But as you look at these two equations, is there some way that I could replace the r? Is there some type of algebra that I can do that I would be able to replace r? The answer is yes. Okay? If I solve this first equation for r, if I add the r over to this side, and I subtract the u over to this side, what do I get? R equals 8 minus u. Right. If I just do a couple of algebra steps, I can solve this equation for r, and now I can replace that r with 8 minus u. Okay? And now that's how I've changed everything over into u. Now, as I look at this, though, we question it right away. Have we made any progress? Does this thing look a lot nicer than this one? Is there a way to take the antiderivative? And as you look at it initially, you probably say no, it looks just the same. I've still got a square root piece in it, and I've still got another function in it. So I really haven't done anything. Okay? But in actuality, we actually have made some progress. Because we now have the ability, if I just take this du and pull it out to the end here, because it's basically just telling me the variable's u. Okay? How did we do an antiderivative like this the other day? If we still have multiplication, how can I do this antiderivative here? What kind of algebra could I do with this? Yeah, I can multiply through. I can distribute through. So I can take this times this, and I can take this times this, and now I will be able to take the antiderivative. Okay, so let's see what that'll look like. And I'll go ahead and multiply everything through right away. Okay, I'm just multiplying right now. So this is 32 times the square root of u. And if I take this times this, I get minus 4 times u to the what power here? This is the first power, this is the half power. So 1.5, yeah. Okay, just add those powers together. 1 plus 1 half. Okay, and so this is something that I can take the antiderivative of. Now, we go back to the original. Could we have done the same thing in the original? Could we have done this algebra at the beginning and not had to do this? And the answer is no. Because can I multiply something like 4r into a square root like that? And the answer is not really, unless if you really are good with algebra and you have a nice way of knowing how do you get something into a radical. Okay? So usually that's not the best option. We substitute to make the square root nicer so that we can take the antiderivative after we do the multiplication. Okay? All right, now let's finish this one off here. Okay? I've got this negative out in front here. Okay, what's the antiderivative of this? Well, the 32 stays there. Antiderivative of this is what? U to the 1.5 divided by 1.5. Okay? Then I come over here, this 4 stays here. What's the antiderivative of u to the 1.5? U to the 2.5 divided by 2.5 plus a constant. Okay? Okay? Notice how I did this. I kept the negative from here. I just kept it out in front because that negative is actually going to have to go through to every single piece here. Okay? And if you wanted to at this stage, you can clean this up. You can divide this out on your calculator. You can divide this out on your calculator. Distribute the negatives through. I mean, there's some things you can do to make it look a little nicer. But this is eventually the result we're after. Okay? And then again, at the very end, we always substitute back in 8 minus r for u so that we have back to the original variable. Okay? So definitely a more complicated example here because we had to use both of these as well as one more equation to get all the substituting taken care of. Okay? All right, so there's that example. Okay, what about this one right here? Okay, this one's a little easier again. Okay? But my question is, there's actually two different ways to do this one, and so I want to just discuss them both and talk about why which one's a little faster than the other. Okay? As we look at this, what would you suggest as my substitution? What substitution do I want to make here? Okay, usually we substitute for the parentheses, sure. Usually I would just substitute 1 plus ln of x, and then what's the derivative of 1 plus ln of x? 1 over x dx, sure. Okay, and does this look like it's going to work pretty well for us? And the answer is yeah. I mean, this is almost a perfect fit. This will just replace the numerator pretty nicely. The 1 over x dx will get replaced pretty nicely with du. This will work. We would be able to finish off the problem pretty quickly here. Okay? Now, is there anything else that could be used as our substitution here? Okay? And the answer is, some students might look at this and they might say, well, I'm just going to substitute u equals ln of x. Okay? Because the derivative of ln of x is still 1 over x dx, and it still matches up pretty nicely here. Okay, now, let's go ahead and do the substitution on both of them and just compare them and see which one is going to be a little easier way to work. Okay, if I come over here to this example, what will my antiderivative look like in terms of u's? The numerator turns into what? This is all u, so this becomes u squared up in the numerator. And then, I've got a 1 here, so 1 over x dx is all the same thing as du. So this changed all the way back to just u squared du. Okay, very simple antiderivative. Okay, all right, what if we try this one over here? Okay, what would this look like if I was just to do my substitutions in this form? Okay, well, the numerator will turn into what? 1 plus u squared. Okay, so this will be 1 plus u squared. And 1 over x dx is still du. So I basically end up with this. Now, as we look at these, we can see this one is much easier to take the antiderivative of. So your choice of 1 plus ln of x was a good choice for substitution. Now, do we know how to do this one, though? Is this something that you would be able to do if I just gave you this problem? And the answer is yes, because if we take and FOIL this out, okay, if I just, off to the side, I take 1 plus u times 1 plus u and multiply it out, I can get this answer in a nice polynomial form and take the antiderivative. So what I'm trying to show you is that there's not always just one substitution that will work. Both of these will work, and they will both get me to the same answer by the time I'm finished. However, my recommendation is this. If you ever have inside a parenthesis like ln of x plus some number, plus a constant, don't be afraid to tack that plus constant onto your substitution, because what's the derivative of any of the constants? The derivative is just 0, so it doesn't change anything. Okay? So it makes problems a little bit easier if you do go ahead and leave that plus 1 on there. Okay? It'll make the antiderivative work out a little bit faster. This one's not bad, but it does take a little bit of extra multiplication. Okay? All right. Have a good weekend, and we'll see you Monday.